Hi, my name is Russ, and I'm the developer of the Ensembles package. This is what I always wanted in terms of doing analytics, AI, data science, predictive analytics, but I never found anywhere, not in open source, not proprietary, anywhere. So I made it myself. This does a lot of cool things that I've never seen anywhere else. And in one word, it does it automatically. This is crazy easy to use. This video is an overview of the numerical function. So we're going to look at numbers, things like prices of houses and stuff like that. Don't worry if you've never done this, you'll be able to follow along. And that's one of the things that makes this really cool is this is going to make that whole analytics, AI, data science world expand enormously. So a lot more people will be able to use it. And if you're a professional in the field already, this will allow you to put results out that many more people can use. So the idea is to expand what people can do and the number of people that can do it enormously. So let's get started with an introduction and overview of the numerical function. So welcome to data science. As we have seen it throughout all the years, it's been something like this. You'll have one lone person, kind of a lone soldier, quite frankly, fighting the battle on their own. What the Ensembles package in general and the numerical function in particular wants to do is make this data science and analytics for the rest of us so that it opens it up to a much larger group of people. And as I said in the intro, if you're a professional, this will expand the number of people that you can work with and make sense with and contact enormously. So think of the Ensembles package kind of like that very first Apple I computer. It was the very first computer where you no longer had to build it before you can use it. Well, starting now, everything in AI data science is going to start working automatically for any numerical data set. In other words, it's like a phone. You don't have to build it or program it before you can use it. Up to now, that's been the case. Starting now, it's going to be completely different, and that's going to be wonderful. This is going to allow you to focus on the story in your data on a foundation of evidence and transparent reasoning, and that's going to give you a lot more power in terms of the results you can deliver to your customer. This is a totally new kind of AI. It's not like anything that's come before. It automates the entire data science process from beginning to end. It's going to automatically use both R and Python, individual and ensemble models, regular and deep learning, and then summarize and return all that all automatically. You just give it the data, answer a couple questions, it does everything. All of the statistical models that's built are returned with no errors, no warnings, no typos, no need for you to correct anything on that side of it. It automatically does the techniques of data science grandmasters, which are ensembles, making it extremely easy for you to use the same techniques and only requires one line of code, which I think is the best part. It automatically uses new procedural AI, literally never uses generative AI to get the best possible results. If you want to think of it as an image, maybe this image might be good. We have been, relatively speaking, in darkness, and what we want to do is bring all kinds of light and openness and transparency to everything. So let's take a look at the ensembles function and open it on up, see what it's like when we go inside. It is, most of all, going to be easy. It's only one line of code, as you'll see. And then it solves everything for you automatically, which I think is the best part. And it's accurate, as you'll see. For example, we're going to beat the results of a published article in Science, but we're going to do some other things too in this video. And fast, you'll be able to see the speed it'll complete everything in just a moment. One goal. The numerical function in the ensembles package is the very best solution in the entire world to any numerical data set in the world, bar none. Same kind of thing, different way. This is the complete and very best solution for any numerical data set. This is not a set of tools to build that solution. A set of tools, for example, might be something like Pandas or ggplot, both extremely good, both used by everybody, obviously including me, to create a solution. This is not that. This is the complete and very best solution. The goal here is to treat you better than any other package ever. Every need you will ever have in an analytic solution has been anticipated and fully met before you even open the package, allowing you to focus on telling the truth in the data. Now, you can reasonably ask, how's that possible? It's possible because whenever people are looking at results from a numerical function, they're asking the same thing over and over and over again. What's the average? How widely spread out is this? How accurate is this? Can I get a visualization? And on and on and on. What people are asking falls into a fairly small number of options, and what the numerical function does is it just collects all of them and returns all of them to you. You obviously don't have to use all of them, but they're available. This is all evidence-based results, totally transparent process, and the results are independently reproducible within the function. You're going to see that in our third and final example. This right here might be the most useful thing to some of you. What most strongly predicts accuracy and independently reproducible results? It's a good question. One of the things that helps is to have diverse ensembles and individual models. If you just have one, then your results are not going to be nearly as good as if you have diverse ensembles or individual models. Secondly, random resampling. The more you do of that, the better. Third, and this is key, reproducible results using the same trained models. I've never seen that done before. So what it's going to do here, and this will be our third example, is we're going to train the models on a given set of data, and then to test it, we're going to use those trained models on totally new data. And if you've never seen this before, just hang on. It's actually really, really cool to see. A few other things that help improve results: if you test or challenge when appropriate, if you ask hard questions, if there's no ego, no pressure, no money, no politics, no force, no deadline, no status, you're not chasing likes. If you start with a goal instead of the truth, accuracy, and accountability, and then you're always willing to admit error and change when the evidence supports it, and if you bring in a nice dose of humility, wisdom, and take the long view and the highest standards, you're going to get much better results than if you do the opposite of all of those. Something important to note: numbers 1, 2, and 3 are the code, the math, all of that. Numbers 4, 5, 6, and 7, whether they go good or bad, depend on people, not the code. Take a look at it. So I'll take care of 1, 2, and 3. I'll get the function as good as it can be. 4, 5, 6, and 7. Down the road, we're going to look at the best ways to work with groups of people, teams of people, stuff like that, to get us the best possible results. Something else that's extremely important is privacy. So the ensembles function in general and the numerical function in particular will never collect personal information, no advertising, no web scraping, no trackers, no bots, no generative AI, no cookies, no information sold, no information shared. There's no pop-ups, no emails, no texts, no reminders, no fake results, no deep fake results. We never save your inputs. I don't care about any of this. Never save your analysis, never save your results. There's nothing to join, no memberships, there's nothing hidden, nothing blocked, no other services are blocked. There's no redirections, no surveys, no polls, no analytics on you, no analytics on your activity, never saving your data. Absolutely no secrets. We're not going to learn a single thing about you, and we won't learn anything about your activity. Now, you might be asking a very good question. Why? It's really simple. If the goal is the most accurate result, none of those things improves the accuracy of the results. So we're not going to do them. It's hard enough to do all this stuff, having written all the code, I know that. I'm not going to add this to my pile of to-do. All I'm going to do is what it takes to get the best possible results. So you provide tidy data, and you'll see that in the next couple of images, answer a couple questions, and then the numerical function is going to automatically return 21 results and a full report. And you'll see all that in just a second. So here's an example of tidy data. This is one of many data sets included in the Ensembles package. This is the strength of concrete. So you see each column, like cement, blast furnace slag, fly ash, so on and so forth. Each column is a feature, each row is an observation, and each cell only contains one output, if you will. So it's not like we have 5 things stuffed into one cell. This is tidy data. The official definition: tidy data is a standard way of mapping the meaning of a data set to its structure. A data set is messy or tidy, depending on how rows, columns, and tables are matched up with observations, variables, and types. In tidy data, which is what you need to use this with, each variable is a column, each column is a variable, each observation is a row, each row is an observation, each value is a cell, Each cell is a single value. You see the link to the source, and my favorite way of putting this is from Dr. Laura Gast, who said, clean data is sexy data. And by the way, she said that as part of the Data Science Hangout. If you're not familiar with it, please look it up. They get together Thursdays at noon Eastern and then record those and post those on YouTube. Amazing, excellent, wonderful. Please join, and if you see me in there, just say hey. So let's look at an example of tidy data. This is what it comes like. And by the way, the concrete data set is included within the Ensembles package. So you can see each column is a feature, each row is an observation. There's only one item in that corresponding intersection of each row and each column. So I've long believed that what we do in this field is best summarized in one sentence from a sentence way older than you and me. It's 2,000 years old, and the sentence says, test everything. Hold on to the good. Again, test everything, hold on to the good. And by the way, that's hardly original with me. That's 2,000 years ago from St. Paul. So let's test what we're talking about right now. Can the numerical function in the Ensembles package beat the best result published in Nature for this concrete data set? The lowest root mean squared error is 4.37. Can we do better? Well, let's take a look. Here is how it works. You load the Ensembles package, and I'll show you how to get it at the end of this video, and then the numerical function, it's going to ask you a couple of questions. First of all, where's your data? Well, the concrete data is included in the Ensembles package, but you can link to external data, that's true. Which column number are we working on? In this case, it's column 9. So let's go back and look at that just a second. If you look, the 9th column, the strength of the concrete, is the column we're interested in. So when it comes back to here, it's going to say, what's the column number? Column number is 9. How many times are we going to resample it? In this case, 2. This is one of many ways that the Ensembles package makes the results more independently reproducible, which is cool. The next several things we're not going to do in this example, we're going to do them all in the third and final example. How to handle strings? There aren't any. Do we have new data? Not this time. We're going to save all trained models? Not this time. Are we going to remove highly correlated features in the ensembles? Not this time. Are we going to use parallels? Not this time. We'll do all that in the third example. So we're going to set up train, test, and validation. 60-20-20 is my choice, but you can do whatever you want. And we're going to run it. It's going to return all of these things. It's going to return a data dictionary. It's going to return the head of the data. And if you note two things, number one, on the far left, the rows are randomized, which is really cool. And number two, on the far right, it changes whatever your target is to the letter Y, and it does that all the time. That's one of the things that makes it work. And it's also going to give you a correlation table. And again, Y on the far right, you can see how strongly correlated each of the features is with the target. Obviously not very strong. It'll give you a data summary, so you can see the minimum, first quarter, median, mean, third quarter, maximum for all this. And it'll build weighted ensembles for you totally, completely, automatically. Now, look at two things on the far left. You see 137, 103, and so on and so forth. The rows in the ensemble are also randomized. And if you look at the very bottom of the second row, Y underscore ensemble, that's the true value. It will also automatically give you the correlations. Now, if you look at these are probably going to be sending off some yellow flags to people who know the field. For example, the very first number there is 0.999. That's extremely high correlation. We're going to see how to deal with that in the third example. It also returns pairwise scatter plots, correlations as colors, correlations as visuals, 3 summary plots at once, but I want to focus on this one. This completely blows my mind. Actual versus predicted. You can be in this business a really long time and never see this. A friend of mine at a conference said, that's not possible. I said, no, this is correct. What's wrong is the training they gave you. That's what's wrong. No one realized this is possible. And when you use ensembles, and as many as we're going to use, and you'll see that in a second, this is definitely possible. It also gives you the residuals. It also gives you a histogram of the residuals. And I realized there's a way to make accuracy plots for each of the 40 models. And just to make this a little more dramatic, I reran this 25 times. So each of the 25 resamplings, you can see the results here. You can see, for example, on the right that LQS is a little more spread around than some of the others. And as it says at the top, root mean squared error by model, lower is better. The black horizontal line is the mean, and the red line is 0. That's your best bet. So you can see the results of all 40 models. It also gives you all 40 models so you can see train, test, validation, and now you can really see LQS is scrambling all over the place. It also gives you a bunch of exploratory data analysis. It gives you histograms of all the numerical data. It gives you box plots of all the numerical data. This one I don't see very often, and I was thrilled that it actually works in general. This is the target versus each of the features. So if you're looking at strength of concrete versus age versus blast furnace slag versus ... No matter how many you have, you don't have to figure it out. It does it for you. It also gives you a summary of all 40 models and their root mean squared error in increasing order. Tells you how long it takes them to run. Tells you overfitting, which you'll see in just a second. And a full summary report. Let's stay with this for just a second. The first column is the name of the model, and the second column, in one word, if you want to think of it this way, is accuracy. So our most accurate model had a result of 0.0589. And the standard deviation there was 0.0117. So it gives you that, but it does that for all 40 of them. It also tells you what the mean of the data is under that model and the standard deviation. Then it tells you something that I think is really cool. It tells you the mean of the train, test, and validation. Think about that for a second. It gives you the mean of the train, test, and validation data sets. So therefore, the accuracy, the number you actually want, is the mean of the test and validation. And in one word, it's the mean of the holdout data. And that's what that second column is, the mean of the holdout data. That's gold. But the better thing is, if you have the mean of the holdout data and you got the training data, then overfitting is just a fraction. It's super easy to figure out. And it also figures out the duration for every single model every time you resample it. So if you resample it 25 times, like I did that one time, it'll do all this and it'll return it for you. And you'll be able to see all of the models. So here are all of the models in one page. You can see some of them are tuned, some of them are not. Some are R, some are Python, some are individual models, some are ensemble models, some are regular learning, some are deep learning. And again, they all run automatically. And by the way, if you happen to like graphic design, I don't know if you've ever noticed, but there's a little shadow at the bottom of the Python logo. See in the comments if you can identify what kind of shadow is. That's kind of cool. In addition, there's no data leakage, no data bleed, no errors, no NAs, no warnings, no missing data. You'll see that in the examples. I'm talking way too much. Let's do some actual real data science here. So we're going to look at the strength of concrete. This is concrete that is really strong. It's like 2,000 years old in ancient Rome. So let's actually do the concrete data set. This you saw before, but next you're going to see it actually run in real time. One of my frustrations when I'm watching tutorials and stuff like that is they'll put a beginning, middle, and end and not actually show it running, so they skip stuff and don't realize it. I want to show you everything. So here is the numerical function running on the concrete data set, and what it does, initially, it's going to put up a couple of data visualizations that you've seen. There's the data dictionary down at the bottom, and then it's going to be running through the individual models and then the ensembles, and then it's going to loop through that a couple of times. And I'll point out a couple of things as this goes on. That using 100 trees, that's not me being super environmentally friendly planting another 100 trees. That'd be nice. That's one of the models. This is XGBoost. XGBoost individual, you'll see XGBoost as part of the ensembles in just a second. And I'll tell you how to separate those apart in just a couple seconds. So now we're going through the ensembles. And like I said, it's running through all this, building all the models, doing all the testing, all of that kind of stuff. And it's going to do one more loop. And again, you can't see this behind the scenes, but obviously since I developed the program, I obviously know how this runs. We're getting close to the end. We got to go through one more iteration of this, and then we'll be all done with, like I said, all 40 models, and then all of the charts and graphs and stuff like that. And we're going to actually see it when it's done. So finish up all the ensembles. Come on, you can do it. There we go. And we're done. So it took less than 90 seconds to do all of that. So let's take a look at what we have. Starting up there, there's the data dictionary right there. Again, I didn't do anything to do all this. It does all this for you. Here's the head of the data, so you can see that. Here is the correlation of the data itself, so you can see that. Here's the data summary, the mean, first quarter, all that kind of stuff. Here is the head of the ensemble, the weighted ensemble. Here's the correlation of the ensemble. And let's go take a look at what it gives us in terms of plots. You can see the three results there. It gives us, the target. It gives us the box plots, the histograms. Again, all automatically. You didn't see me code any of this. It gives me those accuracy plots. Here's my favorite. Again, same kind of just beautiful thing. It gives us the correlation results as both numbers and colors, and the scatter plots, and the full complete report. Everything is here. It did it that fast with one line of code. I think that's crazy good. So let's go forward and take a look at how we did. Our best result was 0.0589, and if you look, 11 of the top 15 results are all ensembles. So how do we do compared to the best result published in that article by Nature? The automatic result from the ensembles package beat the result published in Nature by 98.6522%. And it took less than 90 seconds and only one line of code. I think that's pretty darn good. So let's go to example number 2, which is going to be adding text data. And we're going to use the Carseats data set, which probably many of you have used. So let's start by taking a look at it. And as you can see, 3 of the columns are not numbers. This is a shelving location, and what we're actually going to be looking at is that first column that says sales. We're going to try to create a statistical model for sales. But as you can see, 3 of the columns aren't numbers. So what do you do then? Well, one possible solution is start setting up exactly the same way, load the ensembles package, and then the data is in the ISLR package, Carseats. Column number is 1, because we're looking at the sale price. Let's go back and look at that again. See how it's sales there? It's the first column. That's what we want. Number of resamples is 2. How to handle strings is 1. 0 if there's no strings, 1 if there are. Or if you want to do something, like if you want to do one-hot encoding, you can do that, although this will do that as well. It's going to ask if we have new data. Not this example. We'll do that in the next example. Save all trained models. Not this example. Next example. We're going to reduce ensemble correlations. Not this time. We'll do it next time. And use parallel. Next time, not this time. 60, 20, 20. So there's literally nothing to learn. You already know how to do it. So once you can do one, you can do any similar numerical data set problem in the world. So let's watch it run. So let's get this up and running. So you can see me typing. As you can see, I'm not the world's best typist. This is some of my friends like to joke. This is how long it takes the ensembles package to load on my laptop, which is a couple years old. And I'm going to load the ISLR package so I have access to the data. And we're now going to do the numerical function. So this is how you can pull the data if it's like within a different R package. We're going to look later on how to do it if it's like on the internet or something like that. Column number is 1. That's the sale price. We're just going to resample twice this particular time. How to use strings. We're going to set that up as a 1. Do I have new data? Not this time. We'll do that next time. And then save all trained models. Not this time. We're going to do that in the next example in just a moment. And then it's asking, should we remove highly correlated features? Not this time. We're going to do it next time. So right now, just set it to 1. Use parallel. Not this time. We'll do it next time. And then 60, 20, 20 for train, test, and validation. And I want to set up the timer so we can time and see how long does it take for this to run. So finish up validation right there. And let's have this thing run and see what we got. Anytime you're ready, go ahead and make it happen and start. So let's see how long it takes for this to run. This is something I wish I saw more often on demonstrations in data science. How long does it take to run? So I just put a timer on this thing. And as you can see, we're approaching 15 seconds. It runs exactly the same way as what you saw previously with the concrete data set, which is nice. I like that a lot. So it's very, it's a function. It's consistent. How hard is that to figure out? And, we're just about done. And We are done. 29 seconds. Are there any warnings of any kind? Zero. So there's no warnings, no errors, no mistakes of any kind. Do you get that? In less than 30 seconds, it did all that for this particular data set. And as you'll see me plop on through here, it does all the graphs, all the everything, all done. There's that another, actual versus predicted. And here's the summary report. It's all there from one line of code. I think that's just freaking amazing. So, third and final example. How well do the trained models perform on totally new, unseen data? Game on. Let's do this. This can be a really good challenge. And if you like other methods and other solutions, go ahead with that. So, we're going to go to Boston, one of my favorite places. And I thought it'd be kind of fun to have ensembles over Boston. So, let's do ensembles over Boston. I kind of like this. This actually is a video of Boston, by the way. And then I just said, let me just put ensembles over Boston. Isn't that cool? I like how that looks. Let me fade that out, go back to Boston. Here we are. So the question at hand, we're going to test this, is can the numerical function in the ensembles package beat the top score in a student data science contest? And can we beat it by at least 10% and finish everything in under 60 seconds? As you'll see, the students had, all term to do it. We're going to do it in less than 60 seconds if we can beat this goal. So it is the Boston housing data set, and what we're actually going to be building a model of is the median value of the house price, which is the MEDV value over there. And I'll tell you right now that the average house price in this data set is around $22,500. Now, my friends in Boston are looking at me going, Russ, $22,500 is not the average price of a house in Boston. What $22,500 will actually get you is closer to like parking at Fenway when the Red Sox beat the Yankees. And that would probably be worth it to all my Red Sox friends. But the reason the prices are so crazy low is because this data set is from the year 1970. And therefore, it's been done over and over and over again. So if you want to compare these results with lots of other results, believe me, you got lots of choices. So here is the data science contest. You can look it up. Totally valid. There are 699 entries. And as you can see, they took all spring term to do it. And we're going to see if we can do it in under 60 seconds. So what we're going to do is see if we can beat the score, 2.41243. Let's see if we can do that. Starting with, here's the data on which we're going to train the model. So we're going to use Boston underscore housing, which is a special data set I put in the ensembles package, row 6 down to the end. And what we're going to do is we're going to build all the models on that and train them and everything. And then we're going to check to see how well do they work on this. This top section is totally unseen new data. And we're going to evaluate how well do these same trained models, and that's key, it's the same trained models, work on new data. So what we're going to be looking for is a result of 24.0 for the first one, 21.6 for the second house, 34.7 for the third house, 33.4 for the fourth, and 36.2 for the last. By the way, these are in thousands of dollars. So the first house in Boston cost $24,000. You can go down to Second City here in Chicago and use that for comedy as far as I'm concerned. A house at $24,000 in Boston, that's ancient history. So let's watch this run in real time. And again, what it's going to do is the same thing you saw, but the extra that we're going to do here is we're going to take all those trained models and run them on totally new unseen data and see how close we get to 24.0, 21.6, 34.7, 33.4, and 36.2. So that top section that you see, that's our new data set. I actually have that saved in my hard drive. You'll see that in just a couple of seconds. So what we're going to do is we're going to actually run it. And you're going to see the whole thing. One of my frustrations in watching training videos and stuff is that they would show like the beginning and the end. Like, I get that. I want to see the whole thing, so since I can do this, I'm going to show you the whole thing. That's how long it takes to get the ensembles package running. Boston underscore housing is that special data set I put in the ensembles package. It's rows 5 to the end, so that we can then check our results with the unseen first 5 rows. So you'll see that. And now we're saying, do I have new data? Yes, I do. Do I want to save all trained models? Yes, I do. Do I want to reduce correlations? Yeah, let's reduce them like less than 0.95 so that we're not working with correlated predictors. Are we going to use parallel processing? Yes, we are this time. Now you've got enough experience to see it. And I'm going to use my favorite numbers of 60, 20, 20 so that we've got both, train, test, and validation. And we're going to run it. Let's see how this goes. That's the only line of code we need. Granted, it's got a couple of subsections, but it's the only line of code. This is the third time you've seen this thing, so you have a pretty good idea of how this runs. The first change you're going to see is down at the bottom. It says, what's the URL for the new data? I have it stored on my computer. That's it. That's the new data. This is that 5 rows of data, and now everything looks familiar. So here is that data dictionary. Here's that correlation chart. You can see I'm planting 100 trees again. This is XGBoost again, and so on and so forth. So it's exactly the same thing because it's a function. But the nice thing is it will work with any numerical data set. It doesn't necessarily have to be, strength of concrete or Carseats or the Boston housing. Any numerical data set will work so long as it's a tidy data set. That's on you, not on me. And we are done. That's how fast it ran. It ran the whole thing in that much time. And let's just take a look at a few things. There's the data dictionary, all set. There's the correlation, so you can see, all set. There's the data summary, head of the ensembles, head of the weighted ensembles, actually. There's the correlation. You can see that all of the highly correlated predictors are now gone. It does that for you automatically. It does the graphs, the charts, it does all of that, the accuracy results, everything you've seen before, it's doing automatically. What's different here, oh, I love that, isn't that so good? What's different here is we want to see which model was the most accurate. This time it's something called Bayes RNN, and the most accurate score was 0.1491. Okay, got that. So how did Bayes RNN do on the new data, on the totally new data? Well, it gives you the results not just for Bayes RNN, but for all of them. So for the first house, the true value is 24, and Bayes RNN gave us 23.9288. Second one, 21.6. Bayes RNN gave us 21.6028. Third one's 34.7. This gave us 34.7459. Next one, 33.4. And Bayes RNN gave us 33.3779. Last one, 36.2. And our best model gave us 36.2914. I chose 5 at random. It doesn't have to be 5. You can do 6, 9, 3, whatever. You can do as many as you want. But I've never seen this before, where you're taking the same trained models, testing on new data and seeing how that works. And as you can tell, it's for all of the models. This works. You're standing on solid ground. So my question is, how do we do compared to that best score by the college students? And as you can see, we beat the college students we reduced their error by 97.653%. Took us about a minute. Not too shabby. My hope is if you have any kind of feeling that you feel like this, you're standing on top of a mountain, sun shining on you, everything works, everything's great. So that's a basic overview of the numerical function in the Ensembles package. The Ensembles package does a lot more than this, but this is a very, very good start. If you want to pick it up, right now it's on my GitHub repository. I do need to submit it to CRAN. I have not had a chance to do that yet. I've been too busy writing the package. But you can get it github.com/infinitecuriosity/ensembles with initial caps all over there. That by itself won't work. You're going to need to install it. So one way to install it is to install it using install.packages devtools, library devtools, and then install _GitHub, and then that information. So yes, you do actually have to do something. I'm sorry about that. But that will get the Ensembles package in your system, and then you can start using it. So that's a good overview of the numerical function. You saw 3 fully worked out examples of what it can do, and as you can see, it's incredibly easy. It's just 1 line of code. It's incredibly accurate. I mean, we beat all of those results that were competing, and you saw how fast it was. There's no way I could do all of that stuff that fast, but the numerical function sure can. In the future, I'll be uploading videos about other things that the Ensembles package can do, so keep your eye on it, and I look forward to seeing you at that point. Thanks again for joining today. Leave some comments. We'd be interested in your feedback, and we'll see you in the next video. Bye now.